Great. All right, I'm going to be sort of continuing Tiziana's talk, but with more statistics, looking at a lot more than just those very few most massive objects. So I'll start by talking about black hole growth. So similar things to what Tiziana was talking about, but looking at it statistically. And then I'll end by looking at the Msigma relation. And I'm actually looking at the exact same simulation that was just discussed. So I'm skipping past all the simulation discussion and going straight into results. So this is just showing example growth of several of the most massive black holes, comparable to the ones that were just discussed. But what I was particularly interested in is all of the ones that we look at here really follow the same general trend. So they all start out growing fairly slowly, sub-Eddington. And then they increase their growth rate up to an Eddington rate. They maintain a growth at that point for an extended period of time, and then they slow down. But the question I was asking is, what about the ones that are not the most massive black holes? So I actually looked at that using all the black holes in the simulation. So here is the Eddington ratio plot. So this is just looking at mean Eddington ratio of black holes as a function of their mass. So you can see several different things here. First of all, you see there's a very clear peak. So they start out growing sub-Eddington. The growth rate increases as they grow up until some characteristic mass. And then their growth rate drops. And we find that that growth rate drops at the same characteristic mass, independent of redshift, within the context of our simulation, which is only looking at high redshift. So above redshift 5, it appears to always turn over at this characteristic mass. The other thing that you can see is that it scales like 1 over 1 plus z cubed. So at higher redshift, all the black holes are growing much quicker than at lower redshift. So to look at how that compares with observations, this is looking at the average Eddington ratio as a function of redshift using quasars from Sloan, which are the asterisks, and from our simulation, which is that blue line. So we're very consistent in terms of magnitude and in terms of redshift evolution. And to try and understand why it's evolving like 1 over 1 plus z cubed, we looked at the various properties being used to compute the accretion rate, and we find that it's really due to the gas density. So I've overplotted there the evolution of the typical gas density, and you can see it scales like 1 over 1 plus z cubed. Now, this is not the cosmological gas density. This is the gas density at the center of the halos, where the black holes are actually accreting the gas. And since the accretion rate is directly proportional to the density, the 1 over 1 plus z cubed relation for the gas density corresponds to the same relation for the accretion rate. Taking that a step further, you can see that you have this peak, and that peak is the turnover point of that peak is also a direct result of the gas density. So if you look at the black points that I've plotted on here, that's the average gas density at the black hole. So again, you see that there's a turnover in the gas density, and it's the exact same scale. So what we're seeing is the long-term evolution of black holes on a statistical level is dominated almost entirely just by the black hole density. Obviously, there is interaction with temperature, which affects what density you get. But if you're trying to get a statistical sense, we find that density is really the main property you have to look at. And so to sort of see why that turnover happens, here I've plotted the density profiles of different halo masses from our simulation. And at large scales, meaning at least several kiloparsecs, you can see that as you move into more massive halos, you get higher densities, as you would expect. But if you continue that to the smaller scales, the black hole feedback starts taking over. So above the peak scale that you see here, we actually start suppressing the gas density at the center of the halo. So the more massive halos actually end up with a somewhat lower gas density at the very center because of the very, very high feedback from the black hole. And that's what's causing this general turnover. So just going back to this, you can then see it starts out slow, increases to close to Eddington, and then slows back down again. That's what our general findings are statistically for all the black hole masses. And as Tiziana talked about, you can see the effect in the gas density if you actually plot the local area around some of these objects. All right. So finally, to sort of help understand that scale, you can see on the top axis, that's the typical host halo mass that's hosting these black holes. And you can see that this peak corresponds roughly to the shock heating scale at which incoming gas would be shock heated and makes it much harder to fall into the center and would be more susceptible to black hole feedback. So that's exactly what we're finding here. You're still able to get plenty of cold gas in, especially in the most massive objects where you do have the very, very high density streams flowing in. But we end up with this turnover right around the shock heating scale. Okay, so sort of shifting gears, we also have the Msigma relation from this simulation. And I've looked at that across several different redshifts. So here's actually redshift 7, which is about as high as you can go and still have any significant number of objects. So you can see it's much, much steeper than the local relation, which is the dashed line there. And when we move to redshift 6, we get lots more objects. The slope is still about the same as what we got at redshift 7. It's still much steeper. And then moving down to redshift 5, we have many, many more objects. It's now started to flatten out slightly. If you watch carefully between the two, you can see that going from 6 to 5, it does start to flatten, but it's still about twice as steep as the local relation. So we have quite a few different things that we want to try and look at to understand that, and I'm just going to show you a couple of those things here. So the first thing is luminosity dependence. So it's really important to understand if the Msigma relation has a strong luminosity dependence, because with the very, very few objects at high redshift that we can actually observe, and there being the very luminous objects, we need to understand if we're really probing the right thing. So here I have a luminosity cut in red, and you can see it does match the overall property pretty well. We're pretty much going to get the same slope regardless. If we go to even higher luminosity, we have almost no objects, even though it's not a huge jump in luminosity. But again, the slope is approximately consistent, which suggests that any high redshift observations, even if they do have a high luminosity cut, is going to give us a reasonable slope for the end result. And part of that is simply because of that growth rate that we were looking at before, because the lower mass objects will be actually accreting with a higher Eddington rate, so they will actually often be quite luminous as well. The other thing to help understand is what's happening with mergers. So in blue, which I guess doesn't show up too well, but in blue here, you can see the halos which are undergoing mergers. And it's very clear that it is not the same slope, right? The mergers are almost all low mass objects, but they also are almost all of the objects with unusually high sigma values. So when these halos are undergoing mergers, it's causing a significant increase in sigma. And we actually characterize that statistically across our whole sample by looking at how sigma changes and how the black hole mass changes as a function of time since mergers are happening. So if you look at the dashed line, that's showing the change in sigma, the fractional change in sigma. So you can see just before time 0, at positive time, that's right before the merger occurs. So right before you have the final merger, sigma starts to increase. Over the course of that merger, sigma's jumped up, and then after the merger, sigma doesn't really grow much for a while. The opposite effect is found if you look at what happens to the black hole mass. So as these halos are merging, the black hole mass doesn't grow too quickly. But after the merger has happened, then you're starting to fuel it with a lot of gas, and there's a pretty significant spike in the mass. And it's a nice delay there, which is why you get all of these objects off to the right, because they've undergone this shift in sigma, but have not yet undergone their rapid growth phase for the black hole. So to actually see the paths some of these take, there are 3 red lines here. These are just showing 3 sample histories and how these black holes actually travel along the Msigma plane. So you can see they're very steep. Just like the plot that Tiziana showed, when you're looking at the very massive objects, they do travel in a steeper fashion than the actual relation is in the end. But they tend to travel pretty consistently along the relation. If you switch it and consider ones which undergo major mergers, you get something like this. So you can see in 2 of these 3 cases, there's an enormous jump in sigma, where the velocity dispersion at least doubles. And after that, in fact, sigma actually decreases a bit, and the black hole jumps up in mass. So you can really clearly see the jump straight to the right has almost no has no increase in black hole mass. It's only after that the black hole undergo very rapid accretion. And so the effect of mergers on the Msigma relation is actually quite significant and needs to be dealt with in the simulation as well as in observations. So I'll conclude there that basically when you're looking at how these black holes grow, it really does depend on black hole mass, and that dependency is directly related to the black hole accretion rates, to the local gas density. And when you start getting to more massive objects, the density actually can drop, which is why the accretion rate drops. And you end up suppressing the growth, which is why the most massive objects at high redshift end up leveling off, and they don't continue growing for extended periods of time. And in addition, we have this Msigma relation that's still being looked at right now. We're still working out all the details on how it will evolve below redshift 5, especially with how the distribution of black holes amongst halos does change with redshift, which we've seen in the past. And we're still incorporating that in. But in general, we're finding it's a much steeper relation at high redshift. But you have to be very careful about galaxy mergers really affecting what results you're getting, especially at the lower mass end. So I'll end there.